GameSci.com. GameSci.com.
Let's learn binary. I was lecturing one day at the college I teach at, and the topic was stack traces, sort of the binary trail a computer program leaves as it's executing the code. And a student called me over and said, "You know what? I was a game tester for 5 years at Electronic Arts. I must have generated 1,000 of these stack traces or stack dumps, and I never understood what they meant until now." Very proud that he understood the code and what I was trying to teach him. It made me realize game programmers, almost more than any other type of programmers, really need to understand how binary code executes. Because every time there's a bug, every time there's a problem, they have to go through the binary code to figure out what happened. So I decided to make this first lesson a little bit about binary. The whole course won't be about binary. It's important to have a basic understanding of binary to understand how a computer program executes. So this first lesson will be about binary numbers and how binary code executes on the computer. Let's get started. We as people like decimal are base 10 numbers. Computers, however, like binary are base 2 numbers. Now you can see here that decimal 3 translates to binary 0011. Or decimal 8 translates to binary 1000. Well, how does it translate that way? And why does it translate that way? Let's look at a number and break it down and see how it works. As I said, people like decimal are base 10 numbers, probably because we have 10 fingers. Look at a number like 536. 536 can be broken down. It can be broken down by the formula of 5 times 10 squared plus 3 times 10 to the first plus 6 times 10 to the 0. Well, what does that mean? Well, 10 to the second is 100. So 5 is in what your third grade teacher called the hundreds place. That 5 represents 500. 3 is in what we call the tens place. 10 to the first power is 10. So that 3 doesn't represent 3, it is an actual 30. Finally, the 6 is in what your third grade teacher called the ones place. 10 to the 0 power is 1, so that 6 does indeed represent a 6. Well, if you take the 5 from the hundreds place and the 3 from the tens place and the 6 from the 1 place, you add them all together and it's 536. Because they're decimal numbers, we deal in powers of 10. Computers, however, like binary are base 2 numbers. They don't have fingers, so they don't care anything about 10. Let's look at binary 101. Break it down into 1 times 2 to the second power plus 0 times 2 to the first power plus 1 times 2 to the 0 power. Break that down even further. 2 to the second power is 4. So this is really 1 times 4, or the 4's place. 2 to the first power is 2. So this is really 0 times 2, because it's in the 2's place. 1 times 1, 2 to the 0 power is 1. So this is really just a 1. So we have a 1 in the 4's place, and we have a 1 in the 1's place. 4 plus 1 is 5. Binary 101 breaks down to decimal 5. Now, there's several ways you can learn binary to decimal. I'm going to look at 4 separate ways here. Now, the worst way to learn is brute force memorization. Memorize that decimal 2 is binary 0010. Memorize that decimal 4 is binary 0100. Memorize decimal 7 is 0111. Not a good way to learn. Better to learn how binary works than to try to memorize it. Remember, we're just going to learn enough binary to get us through understanding how a computer program runs. It is not going to be the focus of this entire course. However, could you be a computer expert without being an expert in binary? I don't think so. It's important to understand how binary works rather than memorize binary. Computer science means you understand the entire machine, just not one tiny little aspect of it. So let's learn how binary works. One way you can figure out binary is just generate it with binary add plus 1. Understand this, let's go back to your decimal numbers and remember how you add decimals. I'm going to take the decimal number 999 and get to the next number in the sequence by adding 1 to it. Well, 9 plus 1, there is no digit for that. So we put down 9 plus 1 is 0 with a carry of 1. And you can clearly see I did a carry of 1. That becomes 1 plus 9, which is also 0 with a carry of 1. Which then becomes 1 plus 9, which is a 0 with a carry of 1. So you can see when you add 1 to decimal 999, it comes out to be decimal 1000, as you would expect. Now, we all learn how to do this in the 2nd or 3rd grade. If you remember how to add 1 to all 9s, you might be able to add 1s to binary numbers. Let's switch over to binary. Let's start with a simple binary number of 3. 0011 is binary 3. How do I generate the next number in the sequence? Well, I add 1 to it. And 1 plus 1 is not 2. There is no 2 in binary numbers. 1 plus 1 is just like this 9 plus 1. 1 plus 1 is 0 with a carry of 1. Which means this column then becomes 1 plus 1, which is 0 with a carry of 1. Which means this column becomes 1 plus 0, which is just plain 1. It falls down. And then out here is another 0. So binary 3 adding binary 1 comes out to be binary 4. It's that simple. If you understand 1 plus 1 is 0, carry the 1, you can do binary addition. Let's try it on the decimal number 7. Decimal number 7 is binary 011. Add 1 to it to generate an 8, or get to the next binary number in the sequence. 1 plus 1 is 0 with a carry of a 1. 1 plus 1 is 0 with a carry of a 1. 1 plus 1 is a 0 with a carry of a 1. 1 plus 0 is just plain old 1. So you can see by adding binary 1 to binary 7, I generated binary 8. It's easy. There's nothing hard about it. It might take a little while to generate the numbers, but it's easy to figure out the binary sequence if you learn to add 1. Let's pick it up with that 8. If you want to find out what 9 is in binary, add 1 to binary 8. 0 plus 1 is a 1, and then this 0 falls down, and this 0 falls down, and that 1 comes down. And 8 plus 1 comes out to binary 1001, which is, as you would expect it, 9. So it is pretty easy to generate it. That's better than memorizing the numbers, but let's look at some other ways to figure out binary numbers. There is a pattern for each column. If you look closely, binary numbers follow clear and simple patterns. I've highlighted in blue here the first column, or the 0 column. 2 to the 0 power is 1. 2 to the 0 power is 1, and we call this the ones place. This column is the ones place. And if you look closely, 2 to the 0 is 1, the ones place. It alternates every one digit. If you look down the sequence here, what do we have? We have 0, 1, 0, 1, 0, 1. In the ones place, the binary digits alternate every one. Go to the next column. 2 to the first is 2, or this is the twos place. The ones in this column represent the value 2. It's called the twos place. This one alternates every 2 digits. Look closely. 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. On to infinity. These will alternate every 2 digits because it is the twos place. Look at the third column. 2 to the second is a 4. That's why we call this the fours place. This blue column is the fours place. And the cells alternate every 4 digits. There's 4 zeros, 4 ones, 4 zeros, 4 ones. And off to infinity, they will alternate every 4 places. Finally, let's look at the eights place. 2 to the third power is 8. So this column will alternate every 8 digits. You see 8 digits here, then 2 ones. These ones will go on for 6 more places, or 8 ones, then 8 zeros, then 8 ones. We can see why computers are binary with this example. Binary numbers follow simple patterns, which means binary circuits are simple, small, and fast. They tried to build decimal computers, and the circuits were huge and complicated. We'd much rather build small, simple, fast circuits out of binary than to try to build a circuit that uses decimal arithmetic. The fourth way to generate binary numbers, or binary sequences, is powers of 2 backwards. Now you can see on this red line I've highlighted 2 to the third, 2 to the second, 2 to the first, 2 to the 0. Well, 2 to the 0 is a 1, so I'll write down a 1. 2 to the first is a 2, I'll write down a 2. 2 to the second is a 4, I'll write down a 4. 2 to the third is 8, I'll write down a 2. 8. When I want to convert a binary number like 0, 1, 0, 1, I will write it under the powers of 2. And everywhere I see a 1, that represents a decimal value. So there's a 1 in the 4's column, so I'll write down a 4. There is a 0 in the 2's column, so I won't write down anything. There's a 1 in the 1's column, so I'll write down a 1. 4 plus 1 is 5. And very clearly you can see that binary 0101 is decimal 5. All I have to do to calculate between binary and decimal is write down the powers of 2 backwards. Let's do it again. Let's just write down 8421. Those are my powers of 2 backwards. And let's look at binary 0011. Well, there's a 0 under the 8, so that has no factor in the decimal value. There is a 0 under 4, so that doesn't count. I'll write down nothing. There's a 1 under the 2, and there's a 1 under the 1, so I'll do a 2 plus 1. See, this 1 is in the 2 column. It represents the value 2. This 1 is in the 1 column. It represents the value 1. 2 plus 1 is 3. Voila! I've figured out how to convert binary 3 to decimal 3. Let's do a couple more simple examples. I'll start from the beginning here. I'll write down my powers of 2. 2 to the third, 2 squared, 2 to the first, 2 to the 1. I'm writing these down again so you understand where the 8, 4, 2, and 1 comes. 2 to the third power is 8. 2 to the second power is 4. 2 to the first power is 2. 2 to the 0 power is 1. I want to convert binary 1001 to its decimal equivalent. Well, there's a 1 underneath the 8, so I'll use an 8 in my equation. There's a 0 under 4, there's a 0 under 2, those don't count. There's a 1 under the 1, so 8 plus 1 becomes decimal 9. You know, in technical terms, that 8 represents 1 times 2 to the third power. And that 1 over here represents 1 times 2 to the 0 power. 8 plus 1 is 9. Binary 1001 is equivalent of decimal 9. One last quick example. 8421, my powers are 2 backwards. I want to convert binary 0111. I write that under my powers of 2. There's nothing under the 8, but there is a 1 under 4, 2, and 1, so I'll add 4, 2, and 1 together, and I get decimal 7. You can see it's very easy to go between binary and decimal as long as you understand how binary works. Memorization is the worst way to learn. Understanding how something works is the best way to learn. So let's go the other direction. Let's go decimal to binary. Before we were calculating from the binary value over to the decimal value, let's now go from decimal to binary. And I'll show you 2 ways to do that. Let's convert 6 to binary. The mathematical way to convert 6 to binary is repeatedly dividing by 2. So if I take 6 and divide it by 2, the answer is 3 with a remainder of 0. Make sure you write down the remainders when you do this. With that 3 left over, I'm going to do a 3 divided by 2, which is equal to 1, with a remainder of 1. That 1 left over, I'll say 1 divided by 2, which is equal to 0, with a remainder of 1. What I'm doing is repeatedly dividing by 2 and tracking what the remainder is. And when I'm all done, when I get down to 0, read the remainders backwards. If you start at the bottom here, over here, right here, if you start at the bottom and read this backwards, 110, guess what? 110 is decimal 6. I started with a 6 and I generated a 110. Repeatedly dividing by 2 and looking at the remainder is one way to convert from decimal to binary. To show you how it works, let's do it again. Let's convert 9 to binary this time. So I'll start with 9 divided by 2. 9 divided by 2 is 4 with a remainder of 1. Pretty simple. I'll take that 4 that's left and do a 4 divided by 2, which has an answer of 2 with a remainder of 0. I'll take the 2 that is left and do a 2 divided by 2, which answers 1 with a remainder of 0. I'll take that 1 that is left and do a 1 divided by 2, which the answer is 0 with a remainder of 1. I've reached 0, so I'm done. I'll read this backwards. If you read this backwards, it's 1001. Decimal 9 converts to binary 1001. You can start with 9 and convert it to binary by repeatedly dividing by 2 and looking at the remainder. There is an easy way to do it. Write down your powers of 2 backwards. 8, 4, 2, and 1. Now we're converting 6 to binary. 6 minus 8 doesn't work. 6 does not fit into 8, so I'm going to write a 0 underneath the 8. However, 6 minus 4 does work. So I'm going to put a 1 under the 4. That leaves me with 2 left over. 6 minus 4 is 2. So I'm going to put a 1 under 4 and pick it up with the 2 that is left over. 2 minus 2 is 0. The number 2 fits into the value 2, so I'm going to write a 1 underneath the 2 with a remainder of 0. And I have a remainder of 0, so that last digit will be a 0. All I'm doing is the same thing backwards. What numbers 8, 4, 2, and 1 fit into 6? 4 and 2 make up the value of 6, so I put a 1 under 4 and 2. And you can clearly see that when converting 6 to binary, it comes out 0, 1, 1, 0. Let's do the same thing for 9. Let's convert 9 to binary. 8 fits into 9. So what I'm going to do is put a 1 underneath the 8 and subtract 9 minus 8. I have a remainder of 1, so I'm going to put a 0 under 4. 4 does not fit into 1, so I'll put a 0 under the 4. I still have a remainder of 1. 2 does not fit into 1, so I'll put a 0 under the 2. 1 clearly fits into 1. So 1 minus 1 is 0. Since there is a 1 left over, I'll place a 1 in the ones column of the binary number. And voila! 1001 is decimal 9. Remember, I started with a 9 and I subtracted powers of 2 until I figured out that decimal 9 converts to 1001. So let's boil it down to the quickest way to convert to and from binary. Take the binary value 010011. You want to convert that to decimal. Write down the powers of 2 above it. 32, 16, 8, 4, 2, and 1. And everywhere there is a 1 below a power of 2, add that in as a value of your decimal number. So there's a 1 under the 16, so I'll add 16 into my total. There's zeros under 8 and 4, so they have no effect. There's a 1 under the 2, so I'll add a 2. There's a 1 under the 1's place, so I'll add a 1. Add them all together, 16, 2, and 1. And this binary value, 010011, converts to decimal 19. Easy peasy. There's nothing hard about it. If you remember your powers of 2, and you can write down numbers underneath the powers of 2, you can convert binary to decimal. Let's do it again. I'll write down the powers of 2 first. Then I'll write down the binary underneath it. You can clearly see there is a 1 underneath the 32. So I'll add 32 into my answer. There's a 0 under the 16. That has no effect. There's a 1 under the 8. There's a 1 under the 4. I'll add those two into my answers. With those 3 ones in a binary number, we get 32 plus 8 plus 4. The answer is 44. Binary 101100 is decimal 44. Now, if you prefer to add these vertically, you can see I take the 32, the 8, the 4, put them in a vertical column, and they add up to 44 just the same. How simple is that? Now let's go the opposite direction. Let's go from decimal 19 to binary and see that we convert the exact same thing. 32 does not fit into 19. It never has, never will. So I'm going to put a 0 under the 32. However, 16 does fit into 19. So I'm going to put a 1 on a 16 underneath the 16. And I'm going to do 19 minus 16 is a remainder of 3. Well, I have 3 left over. 8 does not fit into 3, so there's going to be a 0 under the 8. 4 does not fit into 3, so there's going to be a 0 under the 4. However, 2 does fit into 3. 3 minus 2 equals 1, so I'm going to put a 1 under the 2, and I'll have a 1 left over. Since I have a 1 left over, I'll put a 1 in that last column. By the way, just a little hint, if this number right here is odd, then you're always going to get a 1 in this column. That 1 is there because this is an odd number. Now let's do 44. Remember, we're going from decimal 44 to binary. What does decimal 44 convert to in binary? I'll write down the powers of 2 backwards. 32 absolutely fits into 44, so I'll put a 1 under the 32 and subtract 44 minus 32. The remainder, what's left over, is 12. 12 does not fit into 16, so I'll put a 0 under the 16. Is everyone clear why I put a 0 under the 16? Because 12 is what I have left over, and 16 does not fit into 12. However, 8 and 4 do. 12 minus 8 equals 4. Since 8 fits into 12, I'll put a 1 under the 8. Since there's a 4 left over and a 4 fits into 4, I'll put a 1 under the 4. However, after that, there's nothing left, so 2 and 1 get a 0 underneath them. As soon as this number here reaches 0, I'm pretty much done. There's got to be filled with zeros here on the end. So that's a quick and easy way to go from decimal to binary. Write down your powers of 2 backwards and say, ooh, does 32 fit in it? It gets a 1 underneath it. Also point out, this is an even number. If this is an even number, the ones place is very much going to be a 0. That's a little quick check you can do. If what you're trying to convert is odd, there should be a 1 in the ones place. If what you're converting to is even, there should be a 0 in the ones place. If you prefer to do this vertically, and a lot of people do, and I kind of prefer it myself too, you can see I've done it here vertically. I'm trying to convert 44. I'll subtract 32 because it fits and put a 1 underneath the 32. That leaves me with a 12. I'll leave the 16 alone because the 16 doesn't fit into the 12. I'll put a 1 under the 8 because I subtract 8 from 12. I'll put a 1 under 4 because the 4 that's left over, 4 fits into 4 quite nicely. That gets me to a 0, so I'll zero out the rest of the binary number. Decimal 44 converts to binary 101100 in a fairly quick and easy way if I write down my powers of 2 backwards. So let's get to the meat of it, all right? Let's see where binary really affects our computer programs. Let's talk about compiled machine code. Some computer languages are compiled. C and C++ are examples of compiled computer languages. Now, what does that mean, compiled? Well, compiled means we're going to take this code that we wrote. This is code in C and C++. We're going to take this code and convert it over to game.exe, or an executable files. We're going to convert it over before we ever run the program to ones and zeros. That exe is short for executable. In a Windows operating system environment, the exe extension says this code is converted to binary ones and zeros. Now at that point, we don't even need the original source code. The code we typed in has already been converted over to an executable file. We don't need the code that we typed in. What we need now is this executable file, this exe file in Windows. As an executable file, it's binary ones and zeros. I want to make something perfectly clear. The computer does not execute the code we type in. The computers only understand ones and zeros. This code gets converted to this code, machine code or machine language. And it's this code, the ones and zeros, that the CPU executes. A compiled language simply does this conversion before you run the program. So now it's in executable memory. I can say run this program. So what's going to happen is the executable program is going to be taken from RAM memory, loaded into the CPU, and executed. When it's done executing that command, It'll go to the next binary command or the next machine code instruction in memory, load that into the CPU, and execute it. Then it'll go to the next set of ones and zeros in memory, load that into the CPU, and execute it. Let's make this perfectly clear. Executing programs are called machine code or machine language, and they're the binary ones and zeros that the CPU executes. Compiled languages convert to this machine language before you ever run the program. Now let's look at what's called interpreted code. Examples of interpreted programming languages are JavaScript and PHP. An interpreted language is very different than a compiled language. And it has to do with when the ones and zeros are created. So here is an example of JavaScript. You can see that languages are pretty consistent across. An if-else statement is going to look like an if-else statement in between many different languages. The code is required in order to run an interpreted language. You've got to have this source code in order to run the program. What happens in an interpreted language is the executable is created on the fly while you're trying to run the program. The interpreter will read the first line of code, if damage is greater than 5, convert it over to binary machine code, and then send it off to the CPU to execute. When it's done with that, it'll go to the next line of code, health equals health minus 3, convert it to binary machine code, then send it off to the CPU for execution. It'll come back to the program, convert the program to binary machine code. When it's converted to binary machine code, it'll send it off to the CPU and execute that code. See the difference between compiled and interpreted? Compiled pre-builds all the machine code. Interpreted creates it while the program's running on the fly. Now recently we've started to build what we call hybrid languages. Compiled has its advantages, interpreted has its advantages. Compiled languages always run faster because the machine code is pre-built, it's already created. Interpreted languages are always more flexible because you can run them on more computers. Once you compile to a specific CPU, it only works on that CPU, whereas an interpreted language can run on many different computers. So they've come up with these hybrid languages that are both compiled and interpreted. Java and C# are examples of hybrid languages. What happens there is a little bit more complicated, but we're trying to get the best out of both worlds. Best advantages of compiled, best advantages of interpreted. Hybrid language, what happens is we compile the program. But this time we're going to compile the program into a CPU or system independent code. Compiling creates a file like game.class. Game.class would be the Java version, the compiled Java version of this code. This is not machine code. Machine code is specific to a CPU. This is a system independent code. Once the compiler creates the system or CPU independent code, there's no need to access the source code anymore. See this code here? I don't have to send this to my customers in order to run this code. I can send the compiled version, the system independent code, and have them execute that system independent code. When executed, the system or CPU independent code is loaded into RAM. It's sort of a three-step process. You start with the source code, then you go to the system independent code, then you turn it into machine code. That's a hybrid language. Take this system independent code, and a piece of software called the virtual machine will interpret this system independent code into machine language. Once it's in machine language, it'll get loaded into the CPU and executed. The CPU executes the code created by the virtual machine. Once that is done, we'll go to the next set of system independent code, and the virtual machine will interpret the system independent code into CPU specific machine code. From there, it'll go to the CPU and execute that code created by the virtual machine. Finally, the virtual machine interprets the last bit of code here into CPU specific code. The CPU specific code then gets sent to the CPU for execution. Can you clearly see what a hybrid is? We compile into one form and then interpret to the machine-specific machine code. It's the virtual machine. That's the important key ingredient of a hybrid language. A virtual machine sets up a system-independent code that it tries to interpret. That way, we get some of the speed improvement of a compiled language because most of the code has been processed into the system-independent code. And we get the flexibility of an interpreted language because at runtime, it creates the code needed for that particular machine. People want their code to run on multiple computers. Let's look at a very, very simple Java program. Let's look at it in detail. Don't worry if you don't understand exactly everything in this example. In my course, which I teach on ground in a classroom at a college, I tell my students, I show them this code the first day, and I tell my students, don't worry, you're not going to understand all of this until we get about halfway through the class. It's somewhere around the 9th week where I fully explain what this static means. I come back to them and said, okay, we've learned everything we need. So don't expect to know everything about this program from the beginning. Let's just look at it and see how it works. I'm building a public class welcome. I want to put this in a file named welcome.java. Notice that the spelling and the upper and lowercase are exactly the same. If the class is welcome with a big W, then it should be in a file named welcome.java with a big W. Public class welcome. This is the first line of a Java application. This line of code is going to be fairly consistent from program to program. Just get used to it. Java is an object-oriented programming language. Objects are built out of classes, so it's a requirement that we build a class. The one thing that will change on this line from program to program is the name of the program. You don't always have to call your program welcome. You could give it another name. But the public, the class, and this open curly brace will be consistent from program to program. Java applications require what's called a main method, and here we're doing is we're setting up the header of the main method, public static void main, string array args, end of parentheses, open curly brace. This is called the header of the main method. Main is the routine that executes first. When you tell Java to run a program, it jumps to and executes the first line of the main method. The last line of code that executes is the last line of the main method. Again, this is a requirement of a Java program. You have to have a main method. The one executable line of code here is called system.out.println. That's println or print line. And I want to output or print to the screen the words welcome to Java. And you can see on my output here, welcome to Java showed up. This is the only executable line of code in this example, and it says I want to spit out the words welcome to Java onto the console. This closed curly brace matches the closest open curly brace, so this closed curly brace matches to there. So this is the start of the main method, and this is considered the end of the main method. The next curly brace is the end of the class welcome. So see that curly brace? That matches with that curly brace right there. If you're inside these curly braces, you'll be part of the class welcome. If you're outside those curly braces, you will not be part of the class welcome. I know that looks complicated. I know we don't understand what static means. We don't understand what void means. But at this point, we can do what's called monkey see, monkey do program. And that is, if you want to write a new Java program, copy and paste this code. You'll have to change the name of the class because that changes from program to program. You'll have to change that one executable line of code. But the rest of this is just the required structure of a Java application. There's nothing complicated about it. If I were to highlight and paste this code into another program, I could change the name of the class, change that executable line, and I'd be off to the races. There is a simple, straightforward Java program that does something. Prints 3 words to the screen. Don't worry, we'll go out and we'll see a lot more examples. We'll understand this code a lot more by the end of the course than we do now here at the beginning of the course. Thanks for listening to this lesson. We'll see you on the next one. Well, I hope you enjoyed that lesson. Once again, I'm Professor Chris Ferguson. Please visit us at gamesci.com to see more interesting lessons.